Hello, everybody. Good evening. Happy Tuesday. Is it Tuesday? I always forget. Time travels in a straight line, but it feels like it's going all over the place right now. This is Planetarium Live, episode 4. This is our 4th live stream. Things are going great. I'm happy to be here. We're happy to talk together, and I'm going to say hello on the screen. This is me. But I'm also joined by my lovely photo of my lovely friend here. This is Jesse Rogerson's joining us tonight. Say hi, Jesse. Glad you could be here, Jess. And we have a lovely image of you up. So I think so. I think so too. It's the background really brings out your eyes. I don't know. But so a couple of things that always happen when we're joined with a guest. First of all, I'm wearing the headphones tonight, and second of all, we have a lovely stock image because we tried so hard to have Jesse's video on, and last week it took up so much bandwidth that it just kind of killed the stream. So it was kind of a bummer. But now Jesse's here, and that's the important part. His brain is ready to go, and we're going to talk about a lot of fun stuff. So today's episode, we're going to talk about the Comet Atlas. Some interesting things have happened with Comet Atlas. We're going to talk about that. We're also going to do some more Universe Sandbox stuff. I was playing around with some pretty goofy stuff, and I want to show you the results of all of that. And finally, for the last, however, as long as we feel like it, I guess, Jesse and I are going to be asking each other, we're going to be playing a little bit of a game where we tell each other a topic, and the other one has, say I tell Jesse a topic on space, and he has 60 seconds to tell me everything he knows about that topic, and then we're going to discuss it. Now, here's a couple of things about that. We're actually going to set up a poll in the Facebook Live so that everybody out there, while we're doing some of the other topics, you can suggest, you can vote for what we're going to talk about next. Okay, so you get to decide what our 60-second knowledge video stream stuff is gonna be like. All right, so it is kind of like a lightning round, yeah, except lightning strikes a lot faster than that, I think. So so please, everybody who's here, please leave some comments in the chat to say hello so that we know you're here. Check out the poll. We're gonna put up the poll right now, so hopefully we can see it there. Oh, not published yet. We have to publish the poll. There we go, publishing the poll. And there it is. So it's on your screen for Facebook Live, and we can start doing that kind of thing. So the first thing we're going to talk about, Jesse, is Comet Atlas. Now, there was a lot of excitement about Comet Atlas because the comet is getting brighter. It was getting really bright really fast. And I'm actually going to bring up our, we've got a nice, there's a great website here I'm going to show you of tracking this comet. So this comet C2019 Y4 Atlas has been, like most comets, starting out very, very far in the outer solar system and working its way all the way in close to the sun. And as it gets closer and closer and closer, it gets brighter. And as it gets brighter, we can actually see it. And this comet in particular is very, very important because it is brightening really fast. And that's great because it means we could potentially see it without telescopes, without binoculars, without anything really fancy, just with our eyes. Of course, binoculars or a telescope will help it a lot. But something really interesting happened to this comet just yesterday. It was reported by a couple of scientists using a fairly large telescope in Maryland, I believe. They noticed that the comet is actually starting to break up. That's a bad thing. And if we take a look at the brightness curve here, you can see that over the past few days, the brightness hasn't really increased at all. It's kind of getting stuck there, just kind of doing its own thing. And I'm going to show you the photo that we got from that telescope. So here's the photo. And it looks like it's, I'm just going to pull it back for just a hot second. There we go. Okay, so the photo on the left is a couple of days ago. And you can see the comet there in the center. This is called the coma of the comet. That's the big dirty snowball that makes up the comet as we know it. And it's pretty compact. It looks pretty normal. And in the next image, it's getting a little bit bigger, a little bit elongated, a little bit fuzzy. And that generally means that the comet is being blasted apart by the sun. So this is kind of the way comets work, is they're big dirty snowballs out in space, like when you find snow in March, and it's slushy and it's sandy. You know the snow I'm talking about, right, Jesse? Basically. And if you took all of that stuff and made it into a snowball, and it's dripping and sludgy and nasty, and then you made it 4 kilometers across, that's basically what a comet is. And so this comet is coming, as it gets closer and closer and closer to the sun is hot, it's powerful, it starts to blast away the comet. Bits of gas and dust fly off into space and create the comet's tails. And if the comet survives, it gets brighter and brighter and brighter, and we see it looks beautiful. It's great, right? Well, unfortunately, this comet is getting blasted apart by the sun, right? Getting blasted apart by the sun. Oh, interesting. Jesse, I gotta hold on for a second because apparently we're not getting your audio on the stream. So, apparently I can't hear your lovely voice on the stream. So we're gonna try and get this sorted out pretty quickly. But it'll just be a little bit, I think we'll just make it a little bit quiet for a sec, so. Yeah, I think so. And they probably will. Okay, so we'll just let me bring that up for a sec. We'll be right back. Okay, to everybody in the chat, can you hear me now? We'll say yes, probably. Jesse, let's talk a little bit and see if we can hear you. Can you hear us? Can everybody hear? Some people were in the chat. Now they seem to have left. We just need one person. Oh, Jen can hear me, but not Jesse, apparently. Still no Jesse sounds. Okay. Okay, we'll be right back.
Hello. That was Jesse. Can anybody hear me? Oh, wait, you probably don't have it sharing, do you? My video. Right. Video. Gone. Hello, everyone.
Okay. We're going to try this again. People can hear me now. Now let's try the Jesse audio. Say something, Jesse.
Okay. Testing out Jesse's mic. This is the best mic. Ryan's isn't as good as this one.
Did everybody hear Jesse say something there? Yay! We hear Jesse now. Excellent. Okay. Good.
Oh,
that
great.
just proves that my automated tech support is working. Okay, so we're back live. Man, okay, we're going to start that whole comet business again because we were talking about it and everybody just basically heard me talking about it, which is great and all, but Jesse had this really insightful some things that he said that nobody literally heard except for me. So I
feel like everybody should just assume that when they can't hear me, that I'm saying super insightful things.
Basically. And you know what would have been funnier, though, is if I had just, like, brought up the picture of you anyway, you know, like, left this picture of you up, and here it is, it's just silence. And you're just kind of doing your thing, and there's nothing going on. Like, I'm not saying anything, nothing's happening, and there's that picture of Jesse up. So that's, yeah, okay. So we're in business now. So thanks for bearing with us, everybody. Again, a couple things. If you want to vote for a topic for Jesse and I to talk about a little bit later in the show, we've got that poll on the screen in Facebook Live, so you can check that out. And we're already getting a couple votes, which I'm excited about. I'm not going to share the vote with you just yet, but we're going to get to that a little bit later in our show. So let's go back. We were talking about this comet. Now, we got the lovely photo of Jesse up there, but I'm going to bring up this lovely...
It is a great picture.
The one, oh yeah, the one that I'm supposed to be bringing up. The one of the comet. There it is. Okay. So we were talking about this comet. And I mentioned that comets are basically big, dirty snowballs flying through space that are several kilometers wide. When they get closer to the sun, they heat up. That causes gases and dust to come off the comet and creates the tail of the comet. Well, this comet, C2019 Y4 Atlas, is special. It was supposed to be this super bright, beautiful, amazing comet that, if we look at this, you can see the webpage here. If we go down a little bit, you can see its brightness curve right there. That's literally showing how in a very short period of time this comet got super bright. It was going up to, it was on par for like magnitude -2, which is brighter than, almost brighter than the planet Venus, which is pretty crazy. And then just yesterday, some scientists in Maryland took this photo, and what you're seeing is on the left panel, you can see the comet, what's called the coma of the comet, the center of the comet, the dirty snowball, and in the right side of the panel, this is a day later. And what you're seeing is that coma, that comet itself is elongated. And usually that means that the comet is disintegrating. So Jesse, it's time for your insightful comments that you I want you to repeat everything that you said before, word for word.
I'm on it. So it's funny because last time I was on with you, which I think was last Tuesday, you were talking about comets that you had seen. You had seen a comet before. Was it Comet Ison that you had seen?
I had really wanted to see Comet Ison, but I saw one of the Pan-STARRS comets a while back.
Oh, it's Pan-STARRS.
Yeah.
Yeah. In that conversation, we were talking about how many comets get close to the sun and then just sort of fizzle, and they just sort of disintegrate, and all the ice sublimates and it all kind of goes away, and they fizzle out and they're no fun to watch. They disappear, really. And what we're looking at is is the same thing that's going on with this one. It appears that it might fizzle now, and I started wondering on this tangent of why some comets do and some comets don't, because you have these big famous comets like Comet Halley, which I think is on an 80-year orbit, if I'm not mistaken. I should have Googled that.
76
and 76, nice. And that one goes around and around the sun over and over again, and it's been seen multiple times throughout history. You go back 76 years, go back 76 years again and again and again, and there's artwork and there's ancient storytelling. So those ones stick around. That comet sticks around every year. We get the same, or every 76 years we get the same awesome show. So how come that's not happening with this one? Well, it probably is a number of factors, like how close it gets to the sun, which means like how fast it sublimates or fizzles, how much heat it's getting. But probably other things like size, like if it's really big, maybe it's able to hold itself together better, or if its internal composition is different. Like you can imagine when you go to like a rocky beach, at a rocky beach, you might find big, huge boulders that are solid chunks of things, but you also might find big piles of rubble of little tiny things like gravel, so to speak. So if comets can be loose conglomerations of ice and rock, or they can be really compact, dense, hard things of ice and rock, and that would probably affect it too. I don't know how we can actually find out who we would ask. Maybe we could ask Dr. John about something like that. But that was sort of my long tangent to wonder, this one must be some kind of rubble pile.
Yeah, basically. It's, the comets were all formed together at the beginning of the solar system, and so they are basically made of whatever was there, whatever was left in the outer solar system. Lots of ice, lots of water, lots of dust, lots of dirt, and a bunch of other stuff.
Lots of different kinds of ices, right? You got H2O ice, but you also got CO2 ice. You also got NH4 ice, and you have
ammonia.
I feel like I would know more than that, but lots of different kinds of ices.
Yeah, totally. So it appears this comet's disintegrating. It's not getting any brighter. We'll know in about a day or two whether it's going to survive or not, and chances are it's not going to. That's kind of what the feeling is right now amongst the community of astronomers. But so unfortunately,
we were so hopeful.
I know we were. It's just like Ison all over again, except last time. So Ison was this comet. I was telling Jesse this last time we chatted. Is that about 10? I think it was 10 years ago now. I think it was 2010. No, wouldn't be that long ago because I was at because we were at. It was at the Science Center, so it might have been 2015. Anyway, the point is that there was this comet that we knew about it really early on in like January or February, and everybody knew this comet was coming toward the sun. It was going to get its closest approach in December, and this comet went behind the sun from our point of view on Earth. And the idea was that if it survives going around behind the sun and comes out the other side, it'll look beautiful. It'll be bright, it'll be big, it'll be easy to see. It could be the best comet of the decade or maybe even the century. And so the hype around this thing was incredible. And so astronomers, we watched it with spacecraft trained on the sun. We watched this comet go behind the sun, and we waited. And we waited. And we kept waiting. And it never came back. So what ended up happening was it went behind the sun, it disintegrated completely, and then never came out the other side. Actually, all you saw was, I remember the video, because all you saw was a little puff of stuff coming out the other side of what was left of that comet. So yeah, that was disappointing. So I feel a little bit like that right now, but who knows, maybe it'll survive, I don't know. Anyway, that's the deal with that.
There's lots of really great videos of, like, I think NASA has like compilation videos of comets just fizzling out near the sun. I can see if I can find that.
Oh, okay. Sounds good. Just showing the trajectory of the comet as what it was supposed to do. So that's basically it for the comet. The comet. We're basically the end of our comments on the comet for now. I do want to bring up Universe Sandbox because I said I was playing around with it a little bit And I found a really fun animation that I want to bring up for all of you lovely people. So we're going to open this up. It's literally projecting a giant sphere of moons around the Earth, which I think is hilarious because you can kind of see all the different moons here. We pick any one moon. They're all our moon. There's just a lot of them. So we pick any moon. Yeah, look at that. That's our moon. And now we're going to send all of these lovely moons just kind of orbiting around the Earth. And we're going to see what happens. Okay, we're going to slow time down quite a bit. Quite a bit. All right, let's see what happens. So they all start to fall around the Earth, but they're doing something really interesting. They're all kind of... they're getting smaller. There we go. We're going to speed it up just a little bit. They're kind of flattening out. Now, when I saw this the other day, I was pretty confused. And look, some lovely explosions too. That's why we're really here, right? Is to see all these mini moons crashing together as they orbit the Earth and make this big debris field.
That's the point of a sandbox, is destruction.
Yeah, basically, and literally all the supporting work, all the supporting info of this software is like, hey, here's some cool things that you can smash into other cool things to see neat stuff happen. So this is, see all these moons are destroying each other and the Earth and all that fun stuff. But that weird thing was that they all kind of collapsed along the axis of rotation. And it got me thinking a lot about Saturn and Saturn's rings, right? Like if we bring up a brand new simulation, we can bring up Saturn. It doesn't have any rings yet, but that's Saturn. And then what we do is we add in rings. We should add Saturn's rings to Saturn. That's a good idea. So there you go. So we've got these lovely rings here. You can see this lovely ring system. And you'll notice that the rings are actually really thin. I think considering they're about 130,000 kilometers across, they're only about 20 meters thick in some spots, which is not very much. But how did they get
so
like this?
The fun thing about that is, so you're saying 20 meters thick, but 130,000 kilometers wide. That's the same ratio. If you took the ratio of a piece of paper, like an 8.5 by 11 piece of paper, and measure its thickness versus its like length of paper, that the ratio on the rings of Saturn is actually flatter.
No kidding. So if the rings were represented as a piece of paper, the paper wouldn't be thin enough to represent the rings. A normal
exactly.
Piece of paper.
Yes.
Wow. That was. I said it much eloquently than you just did. in order to confirm what you were saying, I said it a lot more poorly. So yeah.
Just said it less eloquently or more eloquently.
Less eloquently, I think. Yeah. So it got me thinking about, how do we get a ring system like this, right? If we started out with a bunch of moons around Saturn, and the idea is that the ring system of Saturn was a captured comet, that Saturn's gravity, tidal forces from Saturn literally tore to shreds, right? Tore to shreds. And so how does it flatten out? And so it got me thinking a lot, and I was telling you a little bit about this, Jesse, before we started the show, that if you're forming a new solar system, it's a big gas cloud, gas and dust kind of flying all over the place, but it does eventually flatten out and spin like a flat disk, which is kind of why our solar system is flat. And if we open up our solar system, we can actually kind of fly around in it a little bit. So like here's our solar system. You'll notice that it is more or less flat. Right, if we zoom right out. Yeah, there's all this other stuff going around, dwarf planets and whatnot. But if you were to look at just the planets of our solar system, they're all orbiting around the sun on this flat plane. So why has this happened? It has to do a lot with angular momentum. Okay, it's this concept that is conserved. And I'm not going to go too deep into this because this is slightly more advanced stuff. But I was thinking about it all morning, so. I've got to at least talk about it a little bit. When a solar system forms, it starts out as this big cloud of gas and dust that's flying in all different directions. Gas is flying one way, dust is flying another one. That cloud, if you add up all the molecules, particles of dust, bits of stuff, if you add up the angular momentum of all that stuff, it's a set amount, a total amount. And no matter what you do to that cloud, no matter how much it shrinks or collapses or collides with itself, that cloud has a certain amount of angular momentum, which is basically kind of how fast everything is spinning around it. Okay? And so what eventually happens is that because it's the same angular momentum, you can have little particles smashing into each other, bouncing off each other, doing all kinds of crazy stuff, but the total amount of angular momentum is always the same. And what ends up happening is it falls into a lower energy state where basically it flattens out and everything is spinning along the same plane with that certain amount of angular momentum. So I want to show you a couple of things to kind of explain this and kind of how I arrived at it. If we bring up the Earth in Universe Sandbox here, we're going to bring up a nice little Earth. We can actually put rings around it, so we're going to just decide to start with, what was I going for? An ordered sphere of stuff. Pause that for a second. So we're adding this ring. You can see it right here. We've got this big ring of basically particles. And if we let the simulation run, you can see that as they orbit, oh, look at that, they're kind of oscillating a little bit. Which is kind of weird. And so, what's the only thing that would stop them from going back and forth like this? The answer is collisions. And so with Saturn's rings, you start out with a bunch of stuff, a bunch of matter all flying around Saturn, and then you get these collisions. And so it's the same thing where we did with those moons before. If we add all those moons, oh boy, we gotta pause this so we can get rid of all these terrible labels and trails and things. The moons do the same thing as the particles, except as they kind of pass through the central part of the disk, they all start colliding with each other, and that slows them down. So eventually, over time, they start to reach equilibrium and form a nice flat disk. Now, you're not going to see that in this video, obviously, in this bit, because all the moons are flying around and smashing into the Earth. You'd have to wait millions and even potentially billions of years. I think Saturn's rings are a couple 100 million years old.
Yeah, Saturn's rings they're actually still on a hugely debated amongst researchers in the field of whether or not they're old or young. But I think the most recent work that I saw was that the rings of Saturn are young, and by young I mean 100 million years, like you're saying.
Yeah.
But my biggest question now, after looking at all the cool stuff that you're showing and all the moons smashing into Earth and destroying everything, is why do some planets have rings and some planets don't? Like, why doesn't Earth get rings? Like, is it size? It might be size.
It might just be.
I feel like the answer.
Yeah.
I don't know.
It might just be the sheer. Well, I mean, look, one thing we've talked about in the past is Earth's mini moon, right? That little asteroid that was car size that basically became a moon of the Earth for like 3 months and then disappeared, right? Or a couple days or however long it was. And in order to actually see rings, you need a lot of stuff. Like Saturn's rings are visible because there's billions of chunks of ice. And so that's important for two reasons, right? We have ice, which is very, very reflective, so you can see it, and there's a lot of it, so it fills up the gaps. But like even in this scenario, like if I bring up a new one and do this again, you know, so we bring back the Earth and we put some particles around it. Add ring. So we add a nice ordered sphere of rings. Add ring, please.
I really got to get this program.
You really do. Like if there's not very many particles,
I need to get it from my Nintendo Switch.
Or if you're really close to it, you can't really see all these particles necessarily. If you're far away, you know, this program is made so that they brighten up. But unless you have a lot of these, you're not going to see them. And I just don't think there's enough big stuff around the Earth to make a ring. I mean, like there's a bunch of satellites. Pardon me?
Like if we go back to the beginning of Earth, when the Mars-sized object smashed into Earth and created our moon, how come that didn't end up creating a ring system? Maybe because everything was close enough that the gravity of the two objects, Earth and the new moon, pulled everything together. Maybe that's what it was.
It could also be stability, right? I mean, rings are short-lived. Like even Saturn's rings are only going to last another couple dozen million years, right?
So we think.
Yeah, right.
They're slowly falling.
Of course, and
Saturn,
the moons of Saturn are pulling pieces away. Some of it's falling into Saturn. They're still colliding with each other and changing constantly and thinning out. So maybe it's just that rings are short-lived. Maybe Earth had a ring for like 1 billion years earlier on in its evolution, and that ring has just slowly dissipated. Now there's nothing left.
So I feel like the answer. I feel like I've heard the answer from John, our friend Dr. John Moores, who is a planetary scientist, that Earth probably never had any rings, but I can't remember why. So now I have to ask him.
Oh, it probably didn't, he said. That's what he said.
That's what I remember. I had this conversation with John, and he said Earth probably never had rings, and I can't remember what the reason was. So now I need to tweet him.
Nice. Okay, I added twice as many moons, and now the simulation's chugging like crazy, so that's fun. But hey, now the Earth is extra destroyed.
That's what a sandbox is for.
Yeah, it really is.
Is for play.
For maxing it out, right?
Yes.
But yeah, so you can do some fun stuff with that. So I don't know. That's kind of the interesting thing. Is I wonder, maybe Earth did have a ring, maybe it never did, but maybe it's just not big enough to hold on to rings, right? Who knows? Okay, I want to talk about this poll, and we're going to come back.
Poll?
Yeah.
I voted on it. Was I supposed to vote on it or not vote on it? Because I did vote on it.
Well, it's up to you. I mean, you're allowed to talk about whatever you want to talk about. But since we're here, for those who have joined us or who were not here during our technical difficulties, one of the things Jesse and I are going to do tonight is this 60 seconds of space kind of thing, where we're going to throw out a topic to the other person. So say I'm going to just blurt out a topic on space, and Jesse has 60 seconds to tell me everything he knows about that topic. And then we're going to discuss it a little bit more to kind of see what we can pontificate about.
Lightning round.
Basically.
Space lightning round.
Yeah, and then we're just going to take turns doing it. So we do have some votes. I'm going to share the results of our poll. And the results show that water on Mars is the popular one. Water on Mars is popular.
Well, how many people voted?
8 people. Which, hey, I'll take it. 8, and look,
Okay.
I can't vote. I'm not allowed to vote. That's a bummer. Anyway, so since I can't vote, I'm just going to say that we're going to reopen the poll, so you can vote on other things or just keep voting on stuff. But water on Mars was winning, and so I think we're going to go with that. So Jesse, you have 60 seconds to talk about water on Mars. Go.
Yeah, I got my cell phone right here, so I'm actually gonna count.
This
it
is
down.
counting
Okay.
as your 60 seconds.
Yes.
And we're going to bring up, and
Okay,
look, the image of you is up. You have to hurry.
Mars is the planet that is next out from the sun than we are, so it's a little further away from the sun, but it is still within a distance that keeps a decent temperature on the surface, and all of the evidence that we've looked at so far on the surface of Mars show that there was probably water there in the past. There are muds and clays that we can find. There are features created like river channels and delta patterns have been found. They have studied the underneath. They found ice, actual water ice, sitting under the soil. They've even seen some briny flows on the surface. So there's evidence of past water. There's evidence of ancient oceans. So we're talking global oceans that are self-sustained, which the best part about it means that the atmosphere was probably thicker and warmer in the past. And that's all I got.
You're beeping.
Yeah.
That was really good. That was really interesting. I brought up a picture of Mars on Sandbox, so we could take a look at it while you were talking.
So obviously, looking at this Mars that you have up there,
Mm-hmm.
it's all reddish, dirty. Like it's big. It's a big, huge desert. There is no liquid water there in any sustained way at the moment.
Mm-hmm.
But features on the ground, images taken by robots, samples of the soil, images from the satellites going around it, all point to a wet history, and that's super damn cool. Mm-hmm. Because water is what makes life happen on Earth. It is the most important part. Well, one of the most important parts of Earth that makes life so flourish here.
Well, look, and when you have one data point for life, like the only life we know in the universe is Earth life, and Earth life need water, right? Like that's it. At least most Earth life needs water. So everywhere
Yes.
else we look, we're looking for water as being kind of the low-hanging fruit of where to hedge our bets and look for life.
It's definitely the number one thing. In fact, like that's basically the 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 general principle that NASA has followed and the CSA has followed on what type of experiments should we be sending to Mars, and how should we be looking for exoplanets out in space, which we're going to talk about later. The general principle, overarching everything, is follow the water.
Yeah.
So how do we find water? What does it look like in our instruments? What type of signatures will show up in the spectra? What type of signatures will show up? The water is the thing. That's what everybody's going for.
It is, and Mars is especially important. So is Venus in that regard, because Mars and Venus are both on the edge of the habitable zone of our sun, right? And so the sun has gradually gotten hotter over time. So millions of years ago, hundreds of millions of years ago, I should say, Venus was not as hot as it is today. Might have been sustainable for life. Mars might be warmer in the future as the sun gets hotter and might be able to sustain life there. So I've actually got the solar system here, and we can actually bring up what we call the habitable zone of the sun.
You can put the habitable zone on?
Any star. So we can see that Earth is in the habitable zone. The habitable zone of a star, since I can't talk tonight apparently, is the place that is the green area on the screen that you're seeing, and that is basically where the amount of heat that you're getting from the sun is not too much to boil water away and not too little to freeze the water. It's just enough that you can have liquid water. And so when we talk about planets in the habitable zone of a star, for whatever star that is, that's the place where they're getting enough radiation from that star to have liquid water. And so that's how we're identifying these planets may have water, they could have liquid water, and so maybe they have life. And so you'll notice with our solar system that Venus is inside the habitable zone now, but I also said the sun was getting hotter over time. And so millions of years ago, the sun was cooler, the habitable zone was closer into the sun, and Venus was actually within the habitable zone of our sun. Now, of course, time has passed. Venus is very, very hot, about 480 degrees on a normal day. Rains acid as well, which is pleasant. But now Venus is not in the habitable zone. Earth is just at the edge, and so of course we have life on Earth. Earth is nice and comfortable and warm, and Mars is also in the habitable zone, but will get warmer over time. And so that begs the question, was there life on Mars in the past when it was wetter and had liquid water? Is it habitable in the future when the habitable zone moves outward and Mars inevitably gets warmer? Too close. Okay. There we go.
So the question here is also really more complicated than it sounds, because as we're finding out with our global climate, the atmosphere of a planet can greatly affect the surface temperature of that planet. So we can say that the sun plays a large role, and it does. It plays a huge role of the ability of Earth to have liquid water on the surface.
Yep.
But the atmosphere of Earth is also a huge part of that story, because just by changing our atmosphere by a tiny amount, by injecting a whole bunch more carbon dioxide, we are able to change its temperature, and that affects life on the planet. And you can imagine if Earth was here but had zero atmosphere, then it would have no life. But if Earth was here and had way too much atmosphere, then it would have no life as well. So there's like this balancing act of distance from the star and type of atmosphere that you have for life.
And that's happened in the past too, right? I mean, the Earth used to have an atmosphere that was mostly oxygen and killed off
mostly carbon dioxide.
No, there was the big oxygenation.
What?
The first oxygen microbes that took CO2 in and produced oxygen, they overran the oceans, and there was far too much oxygen that killed a bunch of sea life.
Oh, I didn't know that.
Yeah,
That's awesome.
yeah, which is kind of crazy. It was one of the great extinction events on Earth.
Oh,
from
cool.
the early history.
I never heard of that.
Yeah, and then of course, life has kind of always engineered the atmosphere to change it, and that atmosphere's changes then affect the life on Earth. So it is this balance where one affects the other, and it's cyclical, right? So that's Mars.
We've done it before. We did it. We're doing it right now with carbon dioxide and other greenhouse gases, but we've also done it before with chlorofluorocarbons back in the
CFCs,
60s, 70s, 80s, the CFCs that messed up the ozone layer. So we are capable. Life is quite capable of engineering and playing with an atmosphere.
Totally. And I'm quite capable of doing it now. So I'm going to fire the Earth at Mars, and there it goes. Goodbye, Mars. Now we have the Earth. Okay, so that was our first one. Let's
Earth's
go to
revenge.
Yeah, right. Jeez. Okay, so let's take a look at our poll again. We're getting some more votes. Let's show our results. So Pluto is now tied for the lead. A couple people voted for the future of the sun too, but Pluto's tied for the lead. So I guess for me it's 60 seconds on Pluto, right?
I'm
so
putting the clock up.
Yeah, okay, you tell me when to go. I'm just going to bring up an image of Pluto on Universe Sandbox, so that I have. Now, I'm not using this to stall and actually have extra time to think about it, although that is kind of awesome. Let's get... And, of course, you see, Pluto's a dwarf planet now, so it doesn't really... I have to find it. Oh, where are you, Pluto? See, there's Planet 9 now, but there's not... I guess it's a dwarf planet.
What?
Okay.
Planet 9?
Oh, it's like a reference to... it's... an artist's impression of Planet 9. So anyway, we could talk about
like
that.
the one that Mike Brown and Badagen.
Yes, have theorized. Yeah, so it has an artist impression as a model in this software. Okay, is the timer ready?
Timer's ready. Are you ready, Ryan?
I'm ready.
3, 2, 1, go!
Okay, Pluto. So, Pluto was discovered in 1930 by a guy named Clyde Tombaugh, who was working at a telescope, and the way he did it was he took a picture of the sky one night, and then the very next night took the picture of the exact same region of sky, and he saw one dot move, and that's how he knew it was a dot within our solar system. All the other stars, being so far away, stayed where they were, but this one dot moved, and that was the discovery of Pluto, which was called a planet at the time. However, Pluto was actually part of this big thing called the Kuiper Belt. Turns out there's a lot of stuff, comets, big icy rocks, all kinds of stuff way out past the orbit of Neptune, along with Pluto. And so this sparked the debate of whether or not Pluto is a planet, especially when the same guy we were talking about a second ago, Mike Brown, discovered Eris, another almost Pluto-sized rock out near Pluto. And so the question was, should they both be planets? Should they not? In 2006, all the big astronomers got together, the oldest astronomers, and they decided that Pluto should not be a planet. We're calling it a dwarf planet. We didn't know what it looked like, but in 2015, I'm just going to keep going. In 2015, New Horizons, a spacecraft, flew past Pluto and gave us the first ever high-resolution pictures of its surface. Pluto has an atmosphere of methane, which we don't know why it should have an active atmosphere. It's got big fields of nitrogen ice that we can see here on the heart region, and it is still forever in some people's hearts as a planet.
That was pretty damn good.
Not bad. I'll take 70 or 80 seconds. It wasn't really about Pluto as much as it was discovery, not a planet anymore, and now on to the, hey, New Horizons found this and this and this. But one thing I do have to say about New Horizons is there's just beautiful, beautiful images. New Horizons was launched in 2006, and it took 9 years of flying in space to travel 3 billion kilometers to Pluto just to take pictures of it. This is an insane amount. Could you imagine 9 years of someone's life plus 10 years to plan that mission? So that's a person's career.
Yeah, and you're saying just to take pictures. The best part about it is that people tend to think when we send a spacecraft somewhere that it's going there and it's orbiting there and we can just turn it around and bring it back, and like the sci-fi, let's fly to Mars, then we'll fly to Venus, then we'll fly to Jupiter. It doesn't work that way.
Yeah.
Most missions, many missions out into space are flyby missions. So not only did it take 9 years to get there, it didn't stop when it got there. It literally just flew by. That's it. It was there. It was able to take pictures of Pluto for like a couple of weeks when it was at its closest approach to Pluto, and then it kept going, and it was done. So this mission that was 9 years of flight, a decade before that of development, this is 20 years. This is someone's career. This is so much work and effort for a 2-week window of images and measurements. Like that's dedication to a science right there.
And it is still the fastest man-made object sent into space. It's traveling faster than any other spacecraft we've ever sent.
Yeah, they really got it going with. They had it on one hell of a rocket when they got it going.
And a gravity assist from Jupiter as well. Really gave it some.
Oh yes, that's right. Yeah.
Yeah. So I brought up Pluto and its moons. Pluto actually has 5 moons, which is kind of neat. People have known about.
And we only have 1.
Yeah, I know, right? Well, 1.5 if you count that little.
One in 1/3000th.
Yeah, right. I want to show you something interesting though about Pluto. That's not that nice. When you look at the trails here, you notice that Pluto has a trail too. Pluto's largest moon, Charon, right here, or Charon, however you want to say it. I say Charon, but Charon is more than half the mass of Pluto. And so what actually that means is that these two objects, it's not like Charon orbits Pluto. The two of them actually orbit their center of gravity, which is somewhere between them. So kind of where the mouse is right now is it's called the gravitational barycenter of Pluto and Charon. So Pluto has 5 moons, but one of them is not even orbiting Pluto technically. So it's kind of weird. Anyway,
have you seen the animated GIF? Okay, I'm putting a thing in the chat.
Okay.
And it blows my mind because there we go. It's a video that New Horizons took on approach that shows Pluto and Charon orbiting each other. It's mind blowing.
Oh yeah? You said you put that in the chat?
I just dropped it in that little chat thing on the side.
So I have yet to see it, but I tell you what, send it, put it in like a chat window to me, because I can bring it up and actually display it on screen so everybody can see it.
Got it.
Excellent, thank you. So I'm going to bring that up so we can take a look at it. Because I'm kind of curious now. Alright, I'm going to share our web content.
Forever curious you are.
Yeah.
My young Padawan.
So here it is. Oh yeah, there you go. Just make sure that shows well on the screen. Yeah, so you can see it. The screen's not moving, but Charon, the smaller dot, and Pluto, the bigger dot, are in fact orbiting their gravitational center point. That is super cool. I do love that. That was on approach from New Horizons, right?
Yeah, that's right. So it was taken in 13 different times, spanning 6.5 days in April before the flyby. Yep.
Wow.
Not this April. April 2015.
Yes, that's right. The flyby was in July, I think, or June, or
sounds right.
Yeah, a couple months. Long ago. It was. It doesn't feel like it's that long ago, but that was 5 years ago now that we had that. So pretty amazing stuff. Okay, so the next one that we got, I'm gonna show the results. Future of the Sun only got 2 votes. I'm disappointed. I thought more people would be interested in hearing how the Sun's going to eventually destroy the Earth, but that's just me.
Fine, whatever.
I think
I don't want to know.
Exoplanets is our next one. So Jesse, I'm going to give you 60 seconds on exoplanets. Now, I'm going to give you a bit of a time primer here because I'll let you set your timer, but I'm going to bring up some exoplanets on Universe Sandbox. Just a quick note to anybody who's been tuning in. Universe Sandbox is really neat software. I'm not actually working with them or anything. I just really like it, and it's pretty fun to just smash stuff into other stuff. And it's really amazing that I can do that and actually make live streams out of it that people are actually watching. So thank you for tuning in, and thank you to Universe Sandbox for giving me something to play around with. But I'll bring up TRAPPIST-1 while you do your thing. So Jesse, are you ready? Your time starts 3, 2, 1 now.
All right, everybody. So my favorite thing about exoplanets. So we know that we live on a planet that orbits a star, and the star that we orbit is the sun, and it's the closest star to us, and so it takes up our sky. It brings us our daytime. But when we go out at night and you look up at that night sky, you see thousands of other stars, and they're stars just like our star. They're bright and they're big and they're burning. They're just really, really, really far away. So the natural question would be, do any of those stars have planets? And the answer is, oh hell yes, they do, because over the last 20 years, astronomers have found upwards of 4,500 other planets orbiting other stars, not orbiting the sun, orbiting other stars. So when you go out at night and you look up at the night sky, it's likely that almost every single one of those stars has not only one planet, but probably more than one planet orbiting it, just like we have a system of planets here. Done.
Well done. That was great. And you're right. It is... to actually be able to look up at the sky and think there's planets. You can actually... There's software that you can use. You know those apps on your phone where it like shows the constellation, it shows you what you're looking at wherever you are, right? You point your phone at the sky or your tablet, whatever you're using.
Okay, what's the best one of those to use?
Oh, geez. There's so many good ones. I mean, it's what...
Okay.
The way I say it, I'm not going to endorse any one in particular. I think you should just get one that works for you, and if you want to spend a bit of money on it, yeah, you'll get extra features. But if you're just going out with family or friends to look at some stars, get any of them and use it. But the neat thing is that some of them actually will show you which stars have confirmed planets. And so I'm gonna throw you a Carl Sagan quote, my favorite Carl Sagan quote. Carl Sagan's a famous astronomer, for anybody who doesn't know that, a famous planetary scientist and astronomer and science communicator. He said that when you make the discovery yourself, you'll never forget it, basically. Even if it's the first time, even if you've never seen it before. So it explains why, I can show you a picture of Saturn and it's exciting, but when you look at Saturn through a real telescope and it's the real planet, you'll never forget that moment. So the idea is that when you're looking up at the sky and you're seeing stars, if you all of a sudden had an app that shows you, hey, there's a planet around that star, that one right there, you can imagine that there's this other planet way out there circling around that star. Does it have life? Does it have water? Is it frozen solid very far away from its star? Is it so close that it's boiling and thousands of degrees Celsius where no life could survive? Are there other planets around that star that we haven't found? Those are the things that you can start to ask, and you'll never forget that moment when you discover it yourself. But one of the things I want to...
I have...
Go ahead.
I have that moment. You said Saturn and its rings?
Yeah.
Do you remember... I have that from undergrad. I think you were there, actually. When we went... Do you remember when we went north of Mac to we brought that telescope and we had a project, an astronomy project? Yeah,
first year astronomy.
Yeah, and I actually saw Saturn for the first time through the lens, through the eyepiece, and I was like, holy crap, this is insane. If you have not seen Saturn with your own eyes through a telescope, it's mind-blowing.
You know what we did for that project was we went back a few different nights, because what we were trying to do is we took photos. We actually had this little crummy digital camera. This is before cell phones even, right? So we had a little digital camera that we held up to the eyepiece of the telescope and took pictures of Jupiter and Saturn through it. And if you do that day by day, you can actually see the 4 big moons of Jupiter and some of the moons of Saturn actually moving, actually orbiting the planet, because they orbit in a period of several days. So I'm actually going to bring up Jupiter and some moons so everybody can kind of see this. But yeah, that's a lot of moons around Jupiter. There's 79 of them now, but the ones I'm talking about are much bigger, much closer. If we zoom right in, bring up some labels. There's supposed to be labels on there, so let's pause for a sec. Yeah, okay, so this is the moon Io. There's 4 of them. Io, Europa is that one. Ganymede, the largest moon in the solar system, bigger than the planet Mercury, and Callisto. Those 4 moons, when you look at them through a telescope, you can actually see them orbiting around the planet over a period of days. So like right now, every second of this movie of the scenario that you're watching, I'll just bring up the orbit so they're easier to see. That's a lot though. Every second of this movie that you're watching is about 4 hours of time. So you can see these little moons puttering around pretty quickly. So what we did basically was we took pictures of the planets and their moons over a few nights, again and again and again, and you can actually make a graph by measuring where the planet was and figure out how quickly they travel around, the moons travel around the planet. So pretty neat, eh?
That's a cool project that you guys did.
It was fun. It was really fun. We did really well on it. It was everything went downhill from there. But so to go back to exoplanets, though, the point I wanted to make is that if you went out outside at night and it's a clear night, and I'm going to actually bring up me for this because I want to actually talk to everybody. If you go outside at night and you hold up the palm of your hand and you try and block out as many stars as you can, at arm's length, you stretch your arm all the way out, you try and block out as many stars as you can, the amount of sky that you've blocked out is about as big as the region of sky that the Kepler Space Telescope was looking at. The Kepler Space Telescope was the first real planet-hunting space telescope. And it was looking in a region of sky about as big as the palm of your hand held at arm's length. And in that region of sky, it found about 3,000 planets out of all the stars that were in, that region of sky. So it found about 3,000 planets. And what that means, though, is that, there's 3,000 planets there, but wherever you put your hand, whether you put it over here or down there or up there, whatever region of sky you cover, that means that there should be the same number of planets around the same number of stars in all directions. So that means that planets are everywhere. And that's really exciting. And then on top of that, of course, Kepler was only able to find planets that were passing in front of their star. Okay, so there's a whole bunch of the planets that are likely there that Kepler wasn't actually able to find as well. So kind of exciting.
There's so many planets. So many planets. There's more planets than there are stars.
Yeah. I mean, there's estimated to be about 1 trillion of them in our Milky Way galaxy. So let's bring up the Milky Way. Our Milky Way's got about 200 billion stars. And each one of those stars should have, on average, 1 to 5 planets, maybe even more. And if you add up all the galaxies in the universe, the 100 billion up to 1 trillion galaxies out there, that means that there's an innumerable amount of planets. And they're constantly being formed. Imagine that every second, several thousand new planets are born. Every second.
Yikes.
Mind-blowing, right? And that's the really cool thing is that, back in the 60s, 70s, 80s, even back, if you want to go to the 50s with the whole Roswell thing in Area 51, right? People were like, oh my god, aliens are so cool. There's aliens out there. It's this amazing thing. Maybe it's real. You can fantasize about going to other worlds and visiting these alien creatures on their home planet. But back then we didn't know that planets were actually there around other stars. Now we know. We know that there are billions of trillions of planets out there. We know that there are planets that are Earth-sized. We know that there are planets that have liquid water and could sustain life. We just have to find the life. That's it.
One day.
Yeah.
I don't know. Do you think we'll ever find it?
Yes, but I think it's very likely to be bacteria and not
the thing
little
is,
gray people.
Like when you're talking about planets around other stars, the resolution that you need to actually finally measure things in its atmosphere, not just we're never going to be able to resolve the surface of these planets. They're too far away. Even the best telescopes can't do that. So we can't take a picture of these planets and see trees, we can't do that.
Yeah.
So you have to rely on the signatures in the atmospheres of these planets. So it might be a point where we get to where we can measure and say that planet's atmosphere has oxygen and methane and H2O and CO2 and I don't know, nitrogen or something. But so it's, if you were to have all that, say you had those, that information sitting on your computer, yes, I can say for sure that this atmosphere of that planet has oxygen, methane, and H2O. Does that mean that you get to say that there's life there?
No, it doesn't. You're still inferring, right?
That doesn't necessarily. You're still inferring.
I think the real search for life is going to happen in our own solar system. I think the search for life is going to happen, in moons of Jupiter and Saturn, in Europa, Enceladus, places where there's life underneath solid chunks of ice, and that life is little bacteria in a vast ocean near a steam geyser deep under the planet. That's where I think we're going to find life. But the important thing to me is that, imagine, Jupiter, a little too close. Imagine we actually do find life on Europa. I'm going to try and find it. Oh, of course, now the moons aren't even showing up. Anyway, imagine we actually did find life on Europa, or even, say, on Mars. That would mean that in our solar system, life arose twice. Okay, and think about this for a second. And maybe it is the same life. Maybe it's the...
Not necessarily.
Well, I know. Just bear with me. Maybe it isn't the exact same life. Maybe it's the same life that is...
You bear with me.
That is hopped over different spots. But if we could find life that potentially arose twice in the same solar system, that would mean that life should be everywhere. And then we can start to make some bigger claims like, hey, maybe those other exoplanets that could harbor life do. And that's pretty likely. We actually have a question in the chat. How close to being Earth-like is Europa? From Charmin
not
Chowdhury.
At all close. No, I mean, so Europa has... Mm-hmm. Sorry?
Go ahead.
So Europa has more water than Earth does, surprisingly. There's more liquid water at Europa than there is at our planet, which is surprising because Europa is smaller than Earth. But other than that, they have nothing else in common. Europa has no atmosphere. It has no rock continents in the way, there's no land in the way that that Earth has land. There is no... the surface is just completely ice. It's just a big ice surface. So the only thing it really has going for it is that it has liquid water underneath all of that ice, and that is somewhat similar to Earth. But other than that, it's very different. There's no magnetic field, there's no atmosphere, all of that stuff.
Yeah, it's far from the sun, right? That's the biggest thing. Is it's so far from the sun. It's not in a habitable zone. It doesn't get a lot of sunlight. But that's not why we're looking for life there. The reason we're looking for life there is that Jupiter is so powerful, that Jupiter has such strong gravity, it creates these massive tidal forces on Europa that causes that moon to stretch and compress and bend and push and pull. And that pushing and pull creates friction. That friction heats up that moon. And so underneath, about 40 kilometers of ice on Europa is a liquid water ocean with more water than the entire Earth. That's why we think that there's life there, is that not only is there water, but that the tidal friction from Jupiter creates a heat source. So now you have two of the things that we think we need for life, a source of energy and liquid water. All that's left is organic material and time. And we know that Europa's been around as long as the solar system, right? 4.5 billion years.
And I'm pretty sure the science on Enceladus, there's better science on Enceladus because Cassini was there.
Yes.
And Enceladus is a similar thing to Europa, and I'm pretty sure that they have organic material from the plumes. And they're able to infer that there's probably volcanic vents at the bottom, underneath the oceans. There would be a rock interface. So if you go from the top of the moon and Europa, you're going to have ice, 40 kilometers of ice, then you hit ocean, and then you have a whole bunch of ocean, and then you hit rock, and then the rock goes through to the center of the moon. So the on Enceladus is a similar situation, except there's plumes, and we're able to measure the stuff that you find in the water. And I'm pretty sure that the science is that they find salty stuff and they find organic stuff, organic meaning carbons and hydrogens, and evidence of volcanic activity underneath all of that water. So, like, it has some cool stuff going for it. It really does. But in terms of like Earth-like, I wouldn't call it Earth-like.
No, not at all. And actually, I'm going to bring up I've got some plumes of Enceladus.
You got some plumes?
Yeah, from the browser.
Some wonderful...
Share the browser window. You can see these are actual jets coming off of Saturn's moon Enceladus, which I've got as well here on Universe Sandbox. This is Enceladus. Moon of Saturn, quite a bit smaller than Europa, as you can see. Enceladus is about 250 kilometers in radius, about 500 kilometers across, and Europa is about 6 times that. So Europa is about 3,000 kilometers across. Quite a bit bigger, a lot more water, a lot more ice, but these are the 2 places, actually aside from Mars, the 2 leading places to look for life in our solar system. And it's
I'm
exactly
super pumped about these
jets. Yeah, I mean, I'm hopeful that in the next decade we will get a mission to Europa. We will get a mission directly to Enceladus that will start to answer some of those questions and at least give us indications. Like, we might find something that says, wow, we need to go there because there is life. So, pretty amazing. Any other questions from chat if you feel like asking? We're just about wrapped up, though. I think, aside from the technical difficulties, we're still over an hour in right now. Jesse, I don't know where this hour went, my man.
It's too fun to talk to you, Ryan.
That's good. I hope I can keep that streak alive and keep you coming back. If you never hear Jesse on the stream again, it means that I have finally bored him to death, and he is...
It's because I was lying the entire time, and I was having a terrible time.
Basically, yeah. And since we're not friends, you can't tell me to my face, right? Okay, so I think we're going to pretty much call it. But that was a lot of fun, aside from the technical difficulties, which I did figure out. But we're going to stream again, hopefully this week. If not Friday, the next Tuesday for sure. And Jesse, you're always invited back just to hang out and talk space.
I'll come back.
And smash stuff into other stuff. We do take suggestions. So you can go on my social media. It's at AstroInAction on Twitter, Facebook.com/AstroInAction, or Instagram at AstroInAction. And hey, I have a YouTube channel too, so I'm going to be uploading this whole video to YouTube in a slightly higher quality, so you can watch me fumble around as I try and fix it from the first 10 minutes. But other than that, if you want to look back on anything that we've talked about, you can see the chat, you can see all the things that we've looked at, and all that kind of fun stuff. So again, a special thank you to Jesse for joining us tonight. Always a lot of fun. Always good to talk to you. And we always find good things to talk about when it comes to space. Not that I'm surprised or anything, but you and I always have a good rapport when it comes to space talk. We've shared a lot of our career together, so we got to continue that on as often as we can.
But just so everybody knows, there is no other rapport out of that. Once we stop talking about space, we have zero rapport.
That is absolutely true. We despise each other when it comes to any other topic. We constantly argue about every other topic. We just agree on space.
Your cats are cool, I guess.
Yours too. And that's it. So thanks a lot for joining for this episode of Planetarium Live. Streaming is still just a lot of fun, but it's really all of you out there who listen, who are tuning in, who make it fun. It's not just us talking to each other about space that's fun. It's answering your questions that's fun. So chat, I expect a lot more questions in the future. Please feel free to join in anytime. I'm going to keep doing this as long as planetarium shows are on the lam. So thanks a lot for tuning in, and I hope to see you again soon. Everybody have an awesome night. Thanks a lot.